Okay, we're going to look into the regioselectivity of a Diels-Alder reaction, and the regioselectivity means the selecting the region where reaction occur. We don't have to look at the regioselectivity if either diene or dienophile, either or, um, is symmetrical. Okay, for example, take a look at this guy. So we start out with the symmetrical diene. You would get this or that. I mean, these are the same compounds. Okay, the same molecules are identical. Uh, this one we start out with the symmetrical dienophile. You will get that. That's the only thing that you get. Now, when both of them are asymmetrical, now we got two options: either leave the aldehyde at the top or put aldehyde at the bottom. Okay, and there's a little bit nomenclature right here. So we have 1,3 product or 1,3 adduct or 1,4 adduct. 1,3 refer to the distance between the electron donating group on the diene and the electron withdrawing group on the dienophile. Okay, so 1, 2, 3 carbons away, 1, 2, 3, 4 carbons away, and the adduct means addition product. Okay, so how do we predict the regiochemical outcome? All right, so we're gonna look at right here. Okay, so we're gonna use the resonance skill that you have learned since OChem 1. All right, it helps so much. Let's take a look. Start out with the diene. We got a methoxy group in it. So the methoxy group, you know, this guy got the lone pair on the oxygen, right? This guy can push electron. It's an electron donating group, or EDG, right? In short, so you can push electron like that. Basically, you can see the negative charge on here, right? So basically, the diene will have electronegative center right there. So this carbon is a little electronegative because of the resonance effect. Okay. Let's do the same way with the dienophile. Now, dienophile got an electron withdrawing group, so you can withdraw and withdraw. Right? You can see there's a positive charge on this carbon. Basically, go back to this original compound. So the dienophile has slightly electropositive on that carbon. Okay, and this happened. The major product is formed. Actually, no. I'll explain this. The reaction prefer where the positive and negative line up closely. Okay, so if I invert the aldehyde group down, look like this, flip it over, you're gonna see that the negative charge right here, that this carbon, which is electronegative, and this carbon, which is electropositive, they line up next to each other. This creates the electronic attraction, and that stabilizes the transition state. Okay, so you get a 1,4 adduct. If you do the other way around, all right, now put this together. Now you're going to see that the negative and positive are further away. Well, of course, they got some interaction, but less than the first one. Okay, and you get 1,3 adduct. Now the first one, since the electronic attraction is stronger because closer, the transition state is more stable, and the faster reaction, so lower activation energy basically. So 1,4 adduct is the major product. Basically, if you have there are multiple regiochemical outcome, you just look at the diene and dienophile, find the positive and negative center. Okay, and when you react them, try to line them up next to each other. All right, I'll give you some example right here. So at the top one, you should be able to do it. We just did together. So negative charge is right there. Okay, and the dienophile, so that's the electron withdrawing group. So I'll just draw one of them. You can do either one. You can draw, you get that and you get that. So the positive charge is right here, is down here. Okay, so when these two react, when they react, I'm gonna line up negative and positive next to each other, so negative and positive, and then do the Diels-Alder reaction. Here we go. Okay, and then you get the product there. So the two aldehyde group is 1, 2, 3, 4 carbons away. This is 1,4 adduct. Right? You don't need to draw the transition state, but I want to draw. Just want to show you. Okay, if you can go from here all the way to the product, go for it. You don't need to draw the transition state. All right, one more. This one, the diene is on the left side, but this is in the S trans, so you have to convert it to S6 first. Okay, keep the stereochemistry the same. That's E isomer. All right, let's see. The negative charge will have to come from the oxygen. So push electron here, here, and here. So at the top. Here we go. That's a negative charge. Okay, the electron withdrawing group, same thing we did together. So the positive charge right here at the end carbon right there. All right, I'm going to line them up, negative and positive. Okay, so put negative and positive together, you get that. So basically the major product would be, yep, this is 1, 2 add up. Okay, so do not memorize that 1, 3 add up is going to be major product, or 1, 4 is going to be major product. Depends on the position of the substituents. Okay, so in this case this is 1, 2, right? In this case this is 1, 4. But the bottom line is, if you know how to line up the positive and negative, that's it. Okay, all right, before we move to the next video, so I just want to expand your knowledge. So this is the Diels-Alder reaction that they people actually do it. Can you identify where the Diels-Alder reaction is? From the top one, if you see diene right here, that's a dienophile. Got the C double bond O, that's electron withdrawing group. The diene got electron donating group, so the lone pair on nitrogen. Okay, so the negative will be down here. If you draw the resonance structure, the positive for the dienophile will be right here. So line them up right there. You get the C double bond O point up like that with the nitrogen 1, 2 add that. It's a Diels-Alder right here. Okay, the next step. So this one we call a cascade reaction, which means the multiple reaction happen right in just one setting. Okay, so that's the Diels-Alder reaction, and then the negative charge right here with the lone pair of on oxygen, put double bond right here, and this double bond attack, that's carbonyl carbon. We will learn this reaction later in a few chapters ahead of us. Okay, and from the second ring right there. Okay, all right, down here we call domino Diels-Alder reaction. So the multiple Diels-Alder reaction happen. So the first Diels-Alder reaction go like that. Here we go, and you get the first ring and the endo rule. Go by endo rule. And there's a second Diels-Alder reaction. Oh, and you get the another ring down there. Okay. Yep, that's interesting. That's how they do it too. You know what? All right, we have another class activity. So same thing. You try to do this. They will reinforce it. We just learned. Okay. So we have question 1, 2, and question 3. Here we go.